Okay, I think we can get started. I want to welcome everybody to the Fall 2021 John and Donna Hall Engineering Lecture. Our speaker today is Claire Tomlin, who is the Charles A. Desoer Chair in the College of Engineering and Professor of Electrical Engineering and Computer Science at the University of California, Berkeley. I'll just say a few words about John and Donna Hall first. John Hall received his Bachelor's of Engineering in Chemical Engineering in 1955 from Vanderbilt. He was a four-year letterman on the football team and a captain in his senior year. He was Vanderbilt's first academic All-American in 1954. After graduating from Vanderbilt, after several years, he went to work for Ashland Oil Company, an oil company located in the Appalachian region, headquartered in Kentucky. And he rose through the ranks in the company to become chairman and CEO. He's been a strong supporter of educational initiatives and institutions throughout the Appalachian region. And there's a very nice documentary that was made about him by the PBS station in Kentucky called John Hall, the Kentucky Commodore. If you just Google Kentucky Commodore, you will find this 1 hour movie video very easily, and it's a really interesting story of John Hall's life. He's a past member and a past chair of the Vanderbilt Board of Trust. He was inducted into the Engineering School's Academy of Distinguished Alumni in 1983. He's married to Donna Stouffer Hall, and that is where the name of the lecture is derived from, the John R. and Donna S. Hall lecture. Together, John and Donna have been great supporters of Vanderbilt and many other institutions in the Appalachian region. I'd like to now introduce our speaker today, Claire Tomlin. Claire received a bachelor's degree in electrical engineering from the University of Waterloo in Ontario in Canada, then a master's degree in electrical engineering from Imperial College London, and then a PhD in 1998 in electrical engineering and computer science from the University of California, Berkeley. Between 1998 and 2007, she rose through the ranks of assistant associate and full professor at Stanford University, which, if you're noticing, that's a very rapid rise through those ranks. Then she was, in 2005, she moved to UC Berkeley, where she currently holds the Charles A. Desoer Chair and is Professor of Electrical Engineering and Computer Science. She's won many awards, but I'll just highlight some of those. In 2019, she was elected to the National Academy of Engineering, and in the same year, the American Academy of Arts and Sciences. In 2017, she received the Institute of Electrical and Electronics Engineers, IEEE, award. Excuse me, one moment, whilst I just, I apologize for that. The Transportation Technologies Award, it was obscured on my screen for a moment there. In 2016, she was awarded an honorary doctorate from the Royal Institute of Technology in Stockholm. In 2006, she received a MacArthur Foundation Genius Grant, and in 2003, the Ekman Award at the American Automatic Control Council. She's also an elected fellow of IEEE and the American Institute for Medical and Biological Engineering. And so it's my great pleasure to introduce Claire to give the whole lecture today. And so I'll now pass this over to Claire. Claire?
Thank you. Thank you so much, Peter, for that wonderful introduction. And I think it's asking me if, yeah, okay, there we go. I'm going to share my screen. And can you see a title screen here? Does it seem to be working? Okay, just holler if it doesn't transition properly. Thank you, Peter. And thanks, Peter and Philippe and Xenophon, for inviting me to give this lecture, which is named for John and Donna Hall. As part of my preparation for this lecture, I watched the 1 hour video about Mr. and Mrs. Hall that Peter has recommended to you, and it's fascinating, and it's just such an honor to give this lecture in their name. I learned many things about John Hall and about his wife Donna. I learned what a Kentucky Commodore is. I learned what a Commodore is, and I learned about a lot about Vanderbilt and Commodores as a result of this video, and then kind of following the train there. So just a great pleasure to give this talk today. Okay, so today I'm going to talk about safe learning in robotics. Now, this is a topic that I have been working on for a number of years, actually since I moved back to Berkeley from Stanford. And the key idea here is, or a key idea here is that machine learning and AI are just booming. The tools and techniques, the methodologies, their applications, it's just growing exponentially, and there's more and more excitement in the application of AI and machine learning tools to real systems. And they've been in use for a long time in real systems, but the approach of using these tools in safety critical systems is fairly new. And that's what I'm interested in, because I've worked in safety critical control systems for a long time. And if we're going to use AI and machine learning in these tools, we want to be able to prove properties or analyze properties and understand properties of these automatic control systems that are using AI and machine learning. So with that, I thought I'd start with a project or a system that I've been working on for my whole career so far, which is that of air traffic control. So this is a plot of aircraft across the United States, and in the lower left-hand corner is just a few hours of high altitude traffic. Each of these moving dots is an aircraft moving around the Oakland Bay Area region. And so it's a wonderful project. It started out with me working with NASA Ames, the engineers at NASA Ames, and a large number of projects that they were currently working on, which were trying to automate what air traffic controllers do manually. So air traffic controllers are responsible for talking to pilots and guiding them from their origin to their destination airports, and doing it safely. Safely means primarily maintaining separation between the aircraft. Okay, so it's like I show on the bottom right, there's a virtual hockey puck around each aircraft that other aircraft are not allowed to violate. This is a wonderful control problem. It's a complex system. There's lots of aircraft. Every sector of airspace which an air traffic controller governs typically has 12 to 15 aircraft at any given time. So it's a multi-agent system, and it's so deeply safety critical that it's a very conservative system. So when we introduce automation, so the flight path from origin to destination can be fully automated, but how do you automate things like collision avoidance between aircraft? And how do you do that in a way that's safe for all possible configurations of the system? So that's a problem that I'd like to sort of introduce with as we go through, and maybe say one more word about it. If we think about like the main role of the air traffic controller as keeping the aircraft separated from each other, we can think stylistically about, a controller that's watching and talking to pilots over radio channels for a scenario like this, where you have aircraft coming together and then, moving along one route towards an airport, for example. How do air traffic controllers manage the complexity of routing these aircraft all at once? Well, they're monitoring all the aircraft, and they typically group them together by potential conflict. Like the two aircraft that are already lined up are kind of blue because they're already controlled, right? They're traveling at the same velocity. So they try to reduce the complexity of the problem by following a finite set of simple control rules, which will get the aircraft into simple configurations that are easier to control. So on the bottom left is a diagram, which I really like. It's a picture of, or it's a kind of a stylistic representation of an aircraft under a typical air traffic control system. So the aircraft are usually flying at the optimal altitude at their average speed, and they may speed up or slow down a little bit. But if the aircraft have to change speed a lot, the air traffic controller will reroute them. They'll just, deviate them from their paths to speed them up or slow down. They'll often use altitude changes, or what's called VFS, for vector for spacing. So the air traffic controllers like to sort of draw on a small, well-understood set of control actions as infrequently as possible. So infrequently deviating the aircraft from their nominal average speed, the thing that's optimal for the altitude that the aircraft's flying at. And they group them together, I think, in terms of a mental model of the system by potential conflict. So this idea of modes in a system, like you have groupings of aircraft and you have particular control modes that each aircraft can be in, is a way to simplify the complexity of many aircraft being controlled at any given time. And now, as the air traffic control system is getting even more complex with the introduction or potential introduction of air taxis and unmanned air vehicles, it's nice to think about maintaining the kinds of structures that have been developed and work in our national airspace system. So, this idea of a multimodal system where you've organized the system by these behaviors or modes, and that within each mode there are the dynamics of the system according to that particular mode. Like an aircraft or a pair of aircraft in a collision avoidance maneuver would be following, in this case, say a differential equation model representing how they're flying according to that particular mode. So in my research group, we work on these so-called hybrid systems. These are hybrid because they're a combination of these kinds of finite state machines, like discrete state models, and continuous dynamics that describe the evolution of the system itself, whether it be a robotic system, whether it be a set of aircraft, or even we do work in biology in modeling cancer processes and using these hybrid systems models for those. So as I said, the air traffic system is getting more complex with the introduction of air taxis and UAVs. These are typically much more automated aircraft than the current commercial jets that are in the air traffic control system. And they're automated. They have cameras and other sensors on board to allow them to fly, to detect other aircraft, and avoid collision with the other aircraft. So this is becoming a very big deal, and this is really where a lot of the AI and machine learning tools are being introduced into automated systems like aircraft. So these two images are from companies that my students have interned in recently. They're both Bay Area companies. Skydio is it's basically like a flying camera. It's a quadrotor aircraft with many cameras around it. And people buy them and they use them to, as far as I can tell, mostly to track themselves when they're doing interesting sporting things, or sort of recording their lives as their action-filled lives. Neuro is developing an automated delivery vehicle. This is a vehicle that's small, it's smaller than a car, and it's not meant for transporting people. It's meant for transporting stuff, or delivering food. So again, this is a fully autonomous vehicle which has cameras on board as well as other sensors, perceiving the environment and controlling itself accordingly. Perception and perception from cameras, that process of taking in images, interpreting those images, and then providing information about what's in the environment is what we call perception. That's being done now by deep neural nets. So that, and that's just taking off. The use of neural nets in computer vision is predominant, and it's going to continue to be predominant. So when we think about integrating such cameras and perceptive systems into control systems, we are going to be integrating these deep neural nets into control systems. And that's a topic of research that I'm very interested in, and we'll spend some time later in the talk today talking about those problems. So with that, let me just say for about the next half hour of this talk, I'm going to focus on two things. The first is I'm going to present a tool that or a methodology that we've been developing in my research group really since the beginning. And that's called the concept of reachability. So this is a tool that we've developed largely to address safety critical control systems, designing an automatic controller for a system so that you can prove properties about the behavior of that control system when applied to the system. And that's the tool that we've been developing and using is called reachability. And I'll introduce it through a number of examples. And then for the second part of the talk, I'm going to present how we and other research groups also have been integrating machine learning methods into automation, and how one might use this concept of reachability as a way to try to do that safely. So in the first part of the talk, the challenge is and has really been on computation. How to compute these reachable sets for multi-agent systems in very high dimensions, yet do it in real time is a challenge. And I'll spend some time showing you some examples where we're working on this. And the second part of the talk, the real challenge is the integration of machine learning methods, we call data-driven methods themselves, and doing it in a safe way. Okay, so let's start with the first part. This slide shows in a stylistic way the concept, the basic intuitive concept of reachability. Okay, so let me describe this a little bit. You should be able to see my pointer as a little arrow. Can you guys see that? You can just unmute and say yes. Yeah. Okay. Great. So this is a kind of stylistic representation of the state space of a system. So let's picture our collision avoidance system for aircraft. Let's just suppose you have two aircraft, and the joint dynamics, the relative dynamics of one aircraft to the other is described by a mathematical model. Here it's a differential equation with a state representing the positions, maybe the velocities of the aircraft, control inputs or the the actions that the pilots or the autopilots of both aircraft are taking, and disturbances, things that you can't model. Maybe with respect to one aircraft, the actions of the other aircraft could be considered a disturbance. Maybe there are environmental disturbances like wind that you know are there, but you don't have a good model for. So the question of reachability is the following. Suppose you had some representation of what it means for that system to be unsafe. Okay, so for collision avoidance, it means the two aircraft are violating those virtual hockey pucks around the aircraft. And suppose that we can represent that unsafe condition as a subset of the joint state space of the system. All right, it just means that, like in our case, we can. The relative position of the aircraft violate what is typically a 5 nautical mile distance away from airports. Okay, so my mathematical model represents the joint dynamics of the aircraft, and this set here, this red set, I'm calling it G at time 0, represents unsafe conditions, conditions that I don't want the system to get into, violating that safe condition. The backwards reachable set is the set of all states, and we can index it by time, the set of all states for which, for all possible control actions, there's a disturbance action which, under the dynamics of the system, results in the system state getting inside that unsafe condition. Okay, so under the joint dynamics of the system, these are states which in time t, even despite the best possible control action you could apply, the system could get into this set. That's what we want to protect against, because if you then stay outside of that region, say you're in the blue region here, or even on the boundary of the set, then you have a guarantee that the system will be safe for at least t seconds. And that's what we're after, is these guarantees. Now, true, they're based on, we're designing this based on the model that we have of the system. But if we make that, even if that model is approximate, if we capture the uncertainty about the system in that disturbance, then we can develop these robust guarantees based on this computation. And moreover, we have a framework, or we've developed a framework for computing these sets. So we have this, control and disturbance. We said if for all possible control actions, there's a disturbance. So it's this concept of two players, control and disturbance, playing against each other in a game, where the disturbance you can model as a player that's trying to force the system into an unsafe region, and the control is trying to do the opposite. So we use game theory to characterize and compute these sets. Okay, so so this is a slide just to say that there is a method that you can develop to first characterize these reachable sets, and you characterize them by solving a particular partial differential equation, which is well known in optimal control, called a Hamilton-Jacobi equation. And this is this partial differential equation. So I know many of you are in engineering, and you've seen PDEs and ordinary differential equations, and perhaps in your courses, or you're studying them in your research. This is a variant for reachable sets of one, and we proved that the reachable set is exactly characterized by the solution of this equation. And it's kind of a neat equation. On the left-hand side, you represent safety or unsafety, first of all, by a function in a higher dimension, this value function j. And then the left-hand side of the equation models how j changes with time, versus the right-hand side, which is describing how that function changes over space. And so then over time, you can compute how that function changes spatially. So that's nice. It's a nice mathematical result, but the challenge is computation, as I said earlier. Here's just a slide indicating what I'm saying, that we're modeling that set implicitly through the zero level sets of a function in higher dimension. And there's a couple of other things that I want to highlight, that, if that set stops growing for some time, it closes off for some reason, your dynamics are such that you get this sort of finite set. We call that controlled invariant. And in fact, any super zero level set, so any kind of over approximation of that, is also controlled invariant, and you can use it for safety. This is what we do when we integrate learning. And then moreover, the more you know about the unknowns, the more you know about the disturbances, the smaller that set becomes, right? The more you know about your opponent, the less conservative you have to be. And we can characterize that mathematically. Okay, so let's just say a few words now about computation. And this has been really the big focus of my lab, is characterizing and then developing over the years methods to compute these reachable sets in high dimensions. My first PhD student, Ian Mitchell, who's now the chair of the computer science department at UBC in Vancouver, he developed as a PhD thesis, and then subsequently when he started his position, a toolbox for computing reachable sets, a mathematical computational toolbox. And this is just a picture, or a couple of pictures, showing properties of this. So he's computing this function j, he's solving this Hamilton-Jacobi equation, and you get kind of nice results, like using this toolbox and computing this function j, you can characterize, for example, the function itself, the sub-zero level sets, and useful information like control. Like if you're at a particular state, the value of j tells you how far you are away from the boundary, how far you are away from violating the safety condition. So how far you are away from two aircraft getting too close to each other using a particular control profile. And often these are non-intuitive sets, like this one here is a kind of an interesting collision avoidance protocol we were working on with NASA. Okay, this is the first example. This was back at Stanford. So here are 4 quadrotors. These are quadrotor, there's 4 rotors on each vehicle. This is, they look kind of big and clunky because we built these. This was before you could go out and buy a quadrotor on every street corner, basically. We built them from scratch. We actually designed the PCBs that were on board each vehicle. And in this experiment, we've got 4 vehicles, and there's 4 students sitting there under that under that tent, and each is joysticking their own quadrotor around. But when the quadrotor gets on the boundary of the reachable set with respect to any of the 3 other quadrotors, the automation on board, which is running that reachable set computation, takes over and applies the control action which will guide the vehicle away from the boundary of the reachable set. Because the computation not only gives you the set, it gives you the best control action to take. It solves the game for you. And on the right-hand side is just a snapshot at one particular time of the data. Around each aircraft, you see 3 zones, that collision zone with respect to the 3 other aircraft. Now, this is an interesting system. There's 4 aircraft. Each aircraft, we typically use either a 4 or 12 dimensional model. So then that's, you know, times 4. It's a big state space. But this is an interesting system where you can decouple the collision avoidance problem. That means you can solve pairwise for each collision avoidance between each vehicle, and then compute that reachable set using only the pairwise relative dynamics. So it decouples naturally into 4 separate problems. And that's unusual, but it's why we were able to solve this and do it in real time. You can also do other things with this calculation. You don't just have to compute avoid sets, but you can compute capture sets, regions in which you're guaranteed to reach a desired trajectory or condition, despite disturbances that may be trying to push you away. The equation is the same, except the min and max are just flipped, and the computation is the same. You can also work on hybrid problems, this problem of switching between different modes of behavior. So here, you can define a target set in one mode and map out the profile of how to reach that target set while avoiding the unsafe set. And if you do the computation using this level set method, this just becomes a simple masking of set. You can do that computation very efficiently using this functional representation of sets that we talked about. So we call these sets of states that reach a desired condition while avoiding an unsafe condition. So you want to reach a trajectory but avoid collision with other vehicles. That's called a reach avoid operator. Okay, so a word or two further about computation. So this slide is basically to say that there's a large community of people working in reachability and more generally the area called model checking in hybrid systems. And I've listed a bunch of different strategies that people have employed for dealing with this curse of dimensionality. When you have high dimensional state space, solving this PDE in such a high dimensional space is a problem that suffers from what's called exponential computation challenge, because each dimension, if you grid up the state space, then each dimension, you have a number of grid points. The more dimensions you have, the more vehicles you put in and the bigger the problem, the more and more points you have to compute the solution at. And it just grows exponentially with the dimension of the continuous state. So I'm going to spend a few minutes talking about the bottom 2 methods. One is how we might actually, if we want to do real-time collision avoidance or real-time reachable set computation, how might we exploit offline computation? So to do some of the computation offline and then use it online. And then the second is how we might actually employ machine learning in the computation of the set itself. That's different from the problem I spoke about at the beginning, which is you've got a perception module in your control system that's using machine learning and you want to integrate it. Now I just want to compute the control law, even if I didn't have any perception module, but I want to use machine learning to compute that. So let me say a few words about that. I noticed that there's some chat messages flashing. But I think by the protocol of this talk, I think what we'll do is leave the questions to the end of the talk, because there's a period at the end where those questions will be collected and answered. Okay, so the first, exploiting offline computation. And I'm going to explain this through a fairly recent project that we've worked on with some of my PhD students, which we call fast and safe tracking, or fast track. And the idea is kind of the middle column here. So on the left is what control theorists like myself typically do. We have these high dimensional models, we do optimal control, we model the, if we can see them, we model the regions around the other vehicles that we want to avoid, and we solve an optimal control problem. But it's slow, we can't do it in real time. On the right-hand side is the kind of robotics motion planning crew. And this is a group that does things very fast by coming up with methods for very simple models, just like point mass models of your system that, give for example, a sequence of points that are conflict-free, and you just connect those with dots. The problem is that if you try to track that with your dynamic system, it's going to be approximate, and you may collide in one of the obstacles. And so that's sort of shown here with this actual trajectory, which is colliding with one of the obstacles. So we asked, could we use our reachability framework to pre-compute a kind of buffer zone between a low dimensional planning model, like a point mass model, and a higher dimensional dynamic model of the system? So now we're looking at the relative dynamics between two representations of the same system, a planning model, low dimension, but very fast to compute with, and a high dimensional dynamic model of the system. And that's something we can compute offline. It's invariant to the environment. It's just, all it needs are the models itself. And so the idea behind Fast Track is to do exactly that, is to compute a buffer zone around a point mass planning model, where that buffer zone represents the worst case error between the high dimensional model and the low dimensional model. Once you have that, you just maintain that set, compute it, store it, and carry it around with you as you're planning in real time with the low dimensional model. Okay, so how do we do that? Well, let's just picture it in this example. So this function here, this is a function we're starting with. It can represent the desired bound between the planning and tracking model. Okay, so we call on the vertical axis, this set is called V of RT. So R represents the radial distance and T is time. And so, you can say, well, maybe I want to have a 0.5 meter bound. Is it possible with that planning and tracking model, or a 1 meter bound? So you could take, for example, slices of that set representing these different desired bounds. And then you can look at those slices. So here are shown those, 3 slices of 0.5 meter bound, which is here, a 0.75 meter bound, and a 1 meter bound. And then we've looked at those sets in a projection of the higher dimensional dynamics, which are just the X position, Y position, and relative angle position. So these are 3 dimensions of the full state space of the actual dynamic model of the system. And then we just compute the backwards reachable set. Okay, so what it's doing here is it's carving out that part of the tracking error bound for which there exists a control such that for all possible disturbances, you can stay within that tracking error bound. And it's based on the models that we're using, but again, we use these sort of robustifications of the models. So what does this say? It says that, well, if you want to stay with the models that we're using, if you want to stay 0.5 meters away from your planning model and stay within that, you're out of luck, because there's no controlled invariant set within the 0.5 meter radius. But there is some within the 0.75 meter, and there is more. There's a larger controlled invariant set inside the 1 meter. And moreover, you have the control law from the calculation, which keeps the tracking model within that distance of the planning model. Okay, so it gives us a way for pre-computing an error bound and a control law for maintaining that error bound as the tracking, as the high dimensional dynamic model follows the fast planning scheme from robot motion planning. All right, so an example of recently of where we've used this is a kind of lab experiment that we did with our quadrotors flying around people. Now, people form a challenging environment for robots because they're typically unpredictable and they're hard to model and they don't stand still. So, so we looked to the community of folks working in robot motion planning, but working on predictive models of pedestrians, how they move in different environments. So models that have kind of tried to record human behavior and fit them to different mathematical representations of how people tend to move when they're in different environments. And one of the models that's quite popular is this, it's actually a Boltzmann model. It comes from the physics Boltzmann model. And what is it saying? Okay, so here's a person, and a person's moving in a room. There's a door over here. The door is a goal. Okay, so we might have multiple goals for the person, but suppose that the system has said, well, people like to move towards doors or desks or tables, so we'll model all of those as goals. So here's one, we call it we represent that goal by a parameter theta. And then this Boltzmann model says that the probability of the next action of the human, whether they're going to turn left or turn right or go straight, is captured by how efficient it is towards the particular goals that you have. So this probability of the human motion is more, or that particular action, UH, is more likely depending on how efficient it is to achieve the goal of moving towards the door. Okay, so that's the efficiency is modeled by this value function Q, and so we decided to employ this model of humans as a representation of our obstacles, but moving obstacles. And moreover, we did a little bit more. We looked at this parameter beta, which is given in the exponential. That's called the inverse temperature coefficient in a Boltzmann model, but it's really representative of the spread of the distribution. So I've tried to picture that in the figure at the bottom where, the most likely actions would be the pink actions, moving in a straight line towards the door. So regions of high probability, where regions of low probability are represented in blue, and beta is kind of representing the spread. So as you become more uncertain of the human's behavior, if they start to move in a way that's irrational towards the thinking about the goal, then the spread of where they'll be in the next step will just increase accordingly. Okay, so we applied this. Here's a lab experiment that we did. This is Jaime Fizak and Sylvia Herbert. They're two recent graduates from my group. And they're moving across the lab, and there's two quadrotors in the scenario as well. Let's see if I can get my cursor again. For some reason, it keeps disappearing. So this is Quadrotor 1 and Quadrotor 2. And I've also put a top-down view of the data, in particular, the Boltzmann model predictions around both Jaime and around Sylvia, as well as the goals of the quadrotors, where they want to be. So they're all trying to cross this room. We have quite a small lab, so they're all moving in a kind of cramped space. So let me just play the video. I hope you can see it. So the quadrotors are taking off. Sylvia and Jaime are moving. Jaime is kind of moving in an erratic way. He's Spanish and he's dancing. Sylvia's just walking across. So you can kind of see that actually reflected as we learn this, we collect data. They're wearing these funny hats with data collection devices on them. So that as we collect data, the spread around Jaime kind of increases because he's moving a little erratically according to the Boltzmann model. But what's more interesting to us, and let's play this video again and now focus on the data in the bottom right-hand corner, is what the quadrotors are doing. These are the little pluses that you see. So they're planning their actions based on fast track, and they're avoiding collision with the predicted motion of Jaime and Sylvia in a way that as the predictions become worse, the spread goes out, and then they have to make more conservative paths around. So you can apply fast track not only like for pre-computed obstacles, but obstacles that you're observing in real time, and moreover, stochastic obstacles or obstacles that are moving in potentially erratic ways. One more quick note about computation, and that's this machine learning method. And I'm really just going to say one. I have actually just 2 slides about this, but this is a very recent project. It's actually just been accepted to the Robotics and Automation Conference this year with Samuel Bansal, who's just graduated also. Is instead of using gridding, like these methods that I mentioned to compute the value function for reachable sets, why don't we train a neural net, a deep neural net, to do this computation instead? So there was an advance last summer in the computer vision community about using sinusoidal neural nets, and Samuel got the idea that that would be a good representation for these Hamilton-Jacobi solutions. Moreover, he said, well, we don't want to have to supervise the learning, so let's design a self-supervised way to solve for, or to compute these neural nets, which will solve the Hamilton-Jacobi function automatically given the initial data. And the key idea is to use as the loss function of the neural net process a function h, which represents the Hamilton-Jacobi function itself with the initial data. So for example, we're using the mathematics we know as a source of supervision for the deep neural net, and the loss function h is one where if you had a truly optimal set of parameters for your neural net, the loss would be 0. So we're just going to use that function as a representation of the loss function itself, and basically ask the network to find the grid points on which we do the computation. And this is, I would say, it's one of the more exciting projects we worked on in my career, because in training this neural net, we're able now, when we computed solutions on the low dimensional problems that we could compute using our grid-based method, we're getting more accurate solutions than we could with the grid-based method. Moreover, we can go to higher dimensions. So here's a 3 aircraft collision avoidance problem. So instead of the kind of pairwise one that I showed you earlier with the quadrotors, here now they're aircraft, and they can't hover like quadrotors can, and you can't decouple the motion of the 3 aircraft. So it's a full connected 9-dimensional problem that we're solving using this, we call it deep reach, for deep neural network solving reachability problems. Okay, in the last, we have about 5 minutes left, and in these last 5 minutes, I'd like to talk about integrating machine learning into these reachable set calculations. So just to go back, what we've done is we've talked about safety critical control problems. We've talked about the reachable set, methods to solve it, and methods to deal with computational complexity. In the solution itself is an understanding that you may be uncertain about parts of the system, and we've incorporated that in the disturbance function. But the question is, could you actually, learn those parts of the system that you're uncertain about over time? And that's really where we started with this, learning dynamic behavior, but doing it in a way that you're learning safely. So kind of like if you're a novice driver, you drive, and you drive conservatively and carefully at the beginning, and maybe not so safely as a result, actually. But as you get better and better as a driver, you start to go less conservatively, because you have a better representation in your mind about what the actions of the other vehicles are going to be and the behavior, and you're more used to driving. So it's that kind of paradigm that we were thinking about. And we started out with a Quadrotor experiment. So here, I'll just introduce this through a few experiments, really. So this is one of our other quadrotors, and here it's just trying to follow an up and down step trajectory in the room. So it's trying to protect its envelope. If it gets near the ceiling, it has to curb its vertical velocity. Similarly, if it gets near the floor. So we have a model of the quadrotor. We computed the reachable set based on that model. And then we took the model away from the quadrotor, and we asked it to learn how to control itself to follow a step trajectory. So in that, this is kind of an artificial experiment, because we actually do have the model of the system. In many cases you do for a dynamic system, right? But as an experiment, we said, what if we take away the model and we ask a learning scheme? In this case, we used quite a simple learning scheme. It's from Zico Coulter and Andrew Ng, called Policy Gradient Sign Derivative, as a method to learn how to control itself to track a trajectory without a model of itself. Okay, so what happens? The quadrotor first drops to the ground because it doesn't have a model of itself. And it doesn't crash because it's got the bottom, it still has its envelope. We gave it its safe envelope. But after a little while, it starts experimenting, right? It wants to follow this step trajectory that's represented on the screen by this blue dash trajectory. And so it realizes, we're talking about it like it's a real person, but it notices that it starts to get better values if it moves a bit higher. Why? Because it's getting closer to tracking this particular trajectory. So we give it the trajectory we want it to track, and it can calculate deviations between where it is and that trajectory itself. But it doesn't know its model, and it has to learn the control law without having a model. But it maintains that envelope. So it's always got the envelope, and it's always got the control law to use on the envelope that keeps it safe. So that's what we're bringing over from the first part of the talk. So in the subsequent work, we started to ask, well, you usually don't only want to do that. You want to be that novice driver who's getting better. You want to be able to become potentially, maybe start out with a conservative reachable set, and then as you know your model more and more, you'll get to a unsafe set, which may be much smaller, maybe much closer to optimal, like the, if the disturbance is known case. And so we have a scheme which we call a kind of online safety guarantee validation that's following in online, it's maintaining a reachable set, and then it's following the trajectories, collecting data about the system as it's flying. And it's asking, it's constantly evaluating the disturbance function. And if that disturbance function is actually bigger than it modeled, then it expands the unsafe set according to a level set, an appropriate level set of the value function that it's pre-computed, so it can do that in real time. And then as it gets more and more data, hopefully over time, it learns more about that disturbance function, and it can shrink to a lower value of the level set of the pre-computed Hamilton-Jacobi function. Okay, so now we'll rerun that same experiment with the quadrotor trying to follow a step trajectory. But this time there's a new disturbance introduced that wasn't taken into account ahead of time. So this is a case where the system had a representation of what the unknowns were, but actually there was something that it didn't model. And in this case, that's just a big fan that's putting a disturbance in the bottom half of the room. And we did an experiment first without the safe learning scheme. And then we turned on the safe learning scheme, the one that shrinks the level set, and did the same experiment. And we've plotted them simultaneously on top of each other here. So this is the experiment. There's my elusive cursor. Okay, so first of all, both quadrotors, there's Kenne turning on the fan. Both quadrotors are superimposed on top of each other. And then over time, so it's going to start coming down again, the fan has produced a large amount of wind in the bottom part of the room. And you'll see them separate. So this kind of ghosted out quadrotor represents, the quadrotor being buffeted around by this wind. Whereas the solid quadrotor is running the safe learning algorithm, which recognizes that there are disturbances bigger than it's observed or bigger than it modeled, and it shrinks the level set to a point where the disturbance it's measuring is the same as the one it used in the computation of the reachable set. Okay, so we are now working on, so these are ideas where, the disturbance is, it's okay, it's kind of well behaved, right? The wind or things you don't model. But what we really want to be able to do now are consider unknown unknowns, right? So you've got a system, again, the problem we spoke about at the beginning when we were talking about perception. And the camera on board the robot is viewing the world, and you may know where you are and where you're going, but you don't know what's going to pop up in between. And you want to be able to control yourself safely despite these new obstacles popping up. Maybe they're stationary obstacles, maybe they're people moving around. And so in our latest work, and this is in collaboration with a computer vision specialist, Jitendra Malik at UC Berkeley, is we're integrating in that control loop a perception module using kind of the latest thing that the computer vision community would use, a convolutional neural net, which is trained. In this case, we trained it solely using simulations of indoor spaces. Stanford releases all these nice databases of indoor spaces, so we trained it on simulated data from Stanford. And then we just took that trained algorithm and we applied it without any change in the kind of maybe a little more gritty, messy indoor environments at Berkeley. And what we did there was to use our reachable set as a kind of protective device, that if there's something that the vehicle doesn't recognize and it's about to collide, there's that safe boundary, which is computed using a SLAM pipeline in parallel with the CNN, with the convolutional neural net, which keeps the vehicle safe in the event that the neural net doesn't recognize, or there's some error in the neural net behavior. Okay, so let me just in the interest of time, I'm just gonna skip over that last video and go to the conclusions. Okay, so in conclusion, we've talked about machine learning while maintaining safety. Safety comes from reachability analysis, and the ability to learn from new information is what we're really interested in incorporating. And we've made a first few steps there. We're really interested in this unstructured environment. So not only stationary obstacles that we saw earlier, but also this kind of scenario where, for example, here's the robot moving, and Varun, who is one of the designers of the algorithm, he just moves and veers right in front of the robot. So how do you even train a network to recognize humans and move accordingly? It's, to be able to get the data to be able to train. Do we use our predictive models? How do we do that? So we're experimenting in many different ways to do that. We talked about hybrid models, this combination of discrete modes and continuous dynamics. And I mentioned at the very beginning that it's, I've talked in this talk about one thread, which is largely robotic systems motivated from air traffic control, where they're safety critical systems, and that's one of the key components that went through the thread. But just to say, as I said at the beginning, that this modeling and paradigm and this kind of intermixing of data-driven methods with mechanistic models is something that we use in a lot of our other research projects as well, including the cancer biology project. And so my last slide is about this project, which we've been working on for a number of years with breast cancer specialists, in trying to so we work with collaborators who do experiments on these cell lines, and then we work on the models, which in parallel are trying to help us understand the networks implicated in these different pathways, and what are the most viable treatments or schedules of treatments based on existing drugs. And so again, here we're using a hybrid system model. This is identified from data to represent the observed behavior that, to escape sort of standard treatments, cells will switch their phenotype. They tend to switch from more basal-like, from more mesenchymal-like cell types to basal-like cell types. And just that representation and then using those models for prediction is something that we've been doing. Okay, so I'd like to thank you, and to conclude by, well, thanking you, and also thanking all of the students and postdocs who've worked on the work that I presented today. Many of them have graduated and moved on to other positions, and so I've indicated those with their affiliations now. But the students who are bold-faced are the students who are still working with me in the lab and have really contributed to a lot of this work. I'll mention Forrest Lane. I didn't get to present his work today, but he is joining Vanderbilt as an assistant professor this fall and is thrilled about it. And I'd also like to thank our funding agencies who have funded a lot of this work. So thank you very much.
Thank you very much, Claire. Thank you very much for a wonderful talk, Claire. I have some questions here that have been posted in the Q&A, and I want to encourage anyone who has questions to put them in the Q&A section. We have one question from Philippe Fauché, actually, who wants to know what happens if these autonomous vehicles, planes, cars, etc., what happens to them if there is a technology failure, for example, computer failure, loss of GPS access, etc.?
Yeah, so that's a really good question. I'll give an example because it becomes very system dependent what happens. But we've worked with NASA on it's called a UTM, so a traffic management system for unmanned air vehicles. And the idea is that, you know, we'd like to try to mimic some of the pathway control, the kind of, you know, highway pipelines that you see in air traffic, but do it for popular regions of UAVs, whether they're doing delivery or they're doing, you know, like bridge maintenance or things like that. And this is coming up in an AirLink program that we're starting at Berkeley to try to link the Berkeley campus with potential air taxi to some of the other UC campuses. The idea is to have, for an autonomous system, is to have like a set of failure modes that, despite the technology, if there's a failure, there's an understood behavior. Like, you know, if there's a complete failure, the thing is going to fall out of the sky. But a technology failure, there should be a different path, or in the UTM case, it's an altitude level, that the aircraft that are not participating anymore, there's a failure, they go to a different altitude. For the UAV problem and also the air taxi problem, we also worked with NASA on they called it the Captain Sully controller. So what happens if you get a failure that is, you know, you've still got some control action, but it's really limited. So it's a where to land function that's an automated where to land function that uses geographical information databases from the cloud, as well as a model that's calculated from the failure, which you can either identify or you can you're sort of indirectly identify by motions, to be able to figure out, you know, what are the reachable spaces that I can land in that have the most hopefully the most negligible effect on the environment around me. For UAVs, crashing is bad, but landing and hurting somebody on the ground is the kind of worst thing that could happen. Mm-hmm. So yeah, it's a big issue, and it's done, in my experience, it's kind of a case-by-case basis.
Okay, okay. We have a question from Mark D'Angelo. For the pilot instructed collision flight test, how is the position truth data obtained, for example, motion capture system, and is it shared through a common ground control station? That seems like a fairly technical question.
For the experiment, again, different based on the different experiments. So the Quadrotor experiments that we were doing early on, we had a common ground station. So the information was being sent back to a ground station. In the experiments that we're doing, and actually with the little crazy flies, where you saw the small quadrotors flying in and amongst some of the students in the lab, again, information was sent to a ground station because they were too small to do the computation that we needed to do. Now, in experiments that we're doing on larger quadrotors, we have all the computation being done on all the sensing and the computation being done on the quadrotors themselves. Is that an answer to the question that you asked, or am I answering a completely different question?
If Mark D'Angelo is there, maybe he can indicate whether that answered his question satisfactorily. If not, Mark, just ask another question, a follow-up question, and we'll ask that one as well. Next question I have here is from Jonah Buchanan. Could your collision detection algorithm be applied to autonomous cars where there would be a lot more dynamic obstacles to avoid in a much smaller space?
Yeah, that's the goal. And in a newer project that we have, we're using for an autonomous car, we're using some of that human prediction methodology to predict the behavior of human-driven cars around, and then designing a control system that is guaranteed to keep the vehicle safe, but not be too conservative. Actually, I mentioned Forrest Lane on this slide, who's coming to Vanderbilt. Some of his PhD work has been in solving a new kind of game, or a new kind of equilibrium for a game called a generalized feedback Nash equilibrium, which is suitable for multi-agent systems. He solves it approximately, but then gets from that a really neat solution that allows you in real time to be able to, based on your kind of observations of how the other vehicles are behaving, quickly identify what the most likely actions of those vehicles are, and then control yourself accordingly using a version of the reachable set, which he calls an eyes closed safety kernel. Like if you lose perception, your eyes are closed, how do you maintain safety for a time period despite the the worst case actions of the other vehicles? So the answer is yes, but it's there's a different formulation that we're using, which is than the one I presented today. I mean, it's a different kind of game we're solving.
I had a question actually. It struck me that these algorithms could be used in animation to plot. You know, if you think about Star Wars movies where they have simulated, obviously, spacecraft moving through complex geometries. Maybe there's a application for this kind of technology in animation for creating complex battle scenes or something like that. Have you thought about that at all?
Well, I have thought about it because for some problems it's been done already. When I started out at Stanford, there was another assistant professor in computational math named Ron Fedko, who is still at Stanford. He's a student of Stan Osher, and Stan Osher is a mathematician at UCLA who works on these level set methods. So when Ian and I developed this level set methodology for solving the Hamilton-Jacobi equation, that was kind of with the guidance of Stan Osher. So when we met with Ron at Stanford, he actually became a co-advisor for Ian, and we worked together on a lot of the applications of this reachable set. Well, okay, so Ron was less interested in reachable sets for control systems than he was in computer graphics, so very interested in computer graphics. And then he consulted for Industrial Light and Magic, which does a lot of the animation for things like, I think they do Star Wars, but he's responsible for the mud in the Shrek movies, when Shrek is taking a mud bath, like the fluid. So he does a lot of that kind of physical dynamics modeling and animation of fluid flow using level set methods, but he's using Navier-Stokes equations instead of Hamilton-Jacobi equations. But a PDE is a PDE, right? So, yeah. Yep.
I'm going to jump ahead because I see that Eric Isty from Carnegie Mellon University has asked a question. And you probably know Eric, I would think. He said, you thought some theory could be helpful. I did not see a lot. Do you have a comment?
He said that he thought some theory would be helpful, or?
I think he said you thought some theory would be helpful. So maybe at some point in the talk you mentioned theory would be useful, and he said, I didn't see a lot of theory. Do you have a comment?
Okay, well, yeah, Eric, there is theory in this. From the beginning of like solving the partial differential equations and how to do that, and then the sort of algorithmic methods to do that, to going forward and decomposing those, and But I agree with the integration of machine learning methods. So in particular, when we integrated a deep neural net to help solve for that PDE, that's experimental and it's working out really well, but it's still experimental. So we have to keep evaluating it and understanding. As I said, it's very new. As we moved into the realm of integrating perception algorithms into a theory-based control loop, what did we do? We don't yet have the tools to prove properties of the neural net itself, but we put a safety envelope around it by having a parallel pathway with a reachable set computed using a SLAM algorithm. Now that's, so you get a proof, right? Because if your neural net pushes you into the reachable set, the control action is going to push you out. So there's that style of proof, but maybe what Eric is saying, and he can ask it a different question if this is not, is that with the integration of machine learning, yeah, we do need some theory, and I completely agree. But right now, a lot of the work is quite empirical and experimental there.
There's quite a few questions in here, and I'm trying to give a broad selection of them. John Wixwell asks, the model you presented for cancer only had a small number of variables. In a recent DARPA-funded in vitro experiment, we showed that the delivery of one cancer drug to a single type of cells led to changes in 2,000 gene expression levels, 3,000 protein concentrations, and 800 metabolite concentrations. What does this say about the complexity and controllability of biology?
Yeah, that's a wonderful question. And I agree. I think that often what we're doing is we're trying to find a set of signals that are most affected or that are most indicative of a cell phenotypic state. And others we're either ignoring because we don't know about them yet, or they're there, but we don't have a keen sense on how they affect the behavior, in our case, we were looking at phenotypic cell state. So we had a small number of markers that were indicative of these different, we had 3 different cell states plus a kind of death state that we were looking at. And the states were this basal, luminal, and mesenchymal. And so the markers that we were using there, they kind of, the high-low values of those markers allowed us to partition up the state space into those cells that were typically luminal-like or basal-like, etc. But we know that's just a starting point. I mean, we know from Rosie's lab's work, and actually the work that her group has done after we published that paper about other signals that that are coming to light that have been not included in that model. We've worked also, using this kind of hybrid system methodology, also on the HER2, which is another HER2 positive breast cancer, and the signaling network for HER2 positive breast cancer. And there, our collaborators in Joe Gray's group at OHSU are, they're using, with Gordon Mills, methodologies to get a whole bunch of other signals. Like we have some subset of about 13 signals we've been working with, but they're now getting a lot of other signals that we'll have access to. But I agree, it's a process.
Another question from Taylor Johnson. Thank you for your sorry, it's scrolled past me here because we're getting so many questions, which is very good. Taylor Johnson, thank you for your great seminar, Professor Tomlin. Aside from hybrid systems modeling in the biological domains, do you see applications of reachability in biological systems?
Yeah, thanks, Taylor. Nice to hear from you. Yeah, I think that yes, but it's a dimension problem, I guess, as we know. That just like from the previous question, that the dimension of the signals that the state dimension in the typical biological systems that we're dealing with are pretty high. And so being able to use reachability again suffers from this state explosion problem. But with a push on computational methods for high dimensions that Taylor's group is doing in addition to ours and other groups around, these reachability problems could be used in biology. And where might they be useful? I think about problems where you're really trying to identify a model from observed behavior of a particular system. And so there, reachability might actually be helpful as a system identification technique, that you develop a model and you ask, okay, what are the reachable sets for some initial conditions? And if they're just not what you observe and experiment, you could perhaps parameterize those reachable sets and ask, how might I use the experimental data to update these sets and therefore update the parameters of the model and get better models. We've done this in a really small notch delta system, but again, I think if we can get a better handle on the dimensionality of the problem, then there'll be more uses for reachability, for example, in that case of system identification.
Haojong Luo from mechanical engineering asked two questions. In a two-flyer situation, suppose one flyer is intentionally trying to collide with the other who is trying to dodge. Does the problem essentially become a chase-escape problem? That's his first question. And the second question was, how much does the physics modeling, that is mechanics of flight, play a role in the problem of reachable sets?
Yeah, those are good questions. And the first question, yeah, if you've got a real dogfight going on, then you can capture that, right? That's what these originally these these pursuit evasion games, the kind of game theoretic scenario that we're using, it was introduced by Isaacs, so the Hamilton Jacobi Isaacs, that Rufus Isaacs, he worked at the Rand Corporation around World War II and was, looking at these dogfight profiles for, one, avoiding and capturing another aircraft. Here we're trying to use it in much more, we're using the same framework, but in a much more gentle scenario where we're asking, maybe inadvertently the disturbance does something which is really worst case that we hadn't thought to model. Can we kind of capture that through the game and then protect against it, where it's not necessarily intentional, it's inadvertent. But of course you can deal with intentional actions as well. Sorry, what was the second question?
How much does physics modeling, that is of the mechanics of flight, play a role in the problem of reachable set?
That's right. So it depends on the problem. Okay, so the answer is it can, but it depends on the problem that you want to solve. If your problem is a detailed envelope protection problem where the vehicle, you're looking at the control system of the vehicle itself and it has to maintain its flight envelope through all sorts of conditions where, the dynamics and the interplay between the airflows are really important, then those should be modeled. As much as you can. But if it's, more like strategic collision avoidance, you don't really need very detailed aerodynamic models. You have kind of, well, it depends on the type of aircraft, but if they're commercial jets, those aircraft are built to be, they're built to have kind of linear control schemes, game scheduled between linear control schemes. So they're modeled quite well with fairly simple, at a kind of an abstract level, you can model them with quite simple dynamics. So it's a good question. I have a colleague that in mechanical engineering, Kaushal Srinath, who works on legged robots, and we're working on a gate switching problem using reachability. So the robot's walking with one gate, and then maybe it has to crouch down and move with another gate. How do you compute the gate transition using reachable sets? Once it's on a gate, it's usually kind of following this stable behavior. But if you want to transition between gates, then that becomes a more high dimensional problem because it's involving many more of the joints in the legged robot. And there the dynamics are important.
Question from Michael Goldfarb from Mechanical Engineering. Great talk, Claire. I understand that the air traffic control problem is just an example, but it seems that in that case, avoiding collision is more algebraic than dynamic. That is not clear that the system dynamics are important in avoiding collision, but I could be wrong. To what extent is an optimal control approach appropriate for an algebraic problem?
Yeah, that's a really great question. And hi, Michael. It's nice to hear from you. It is a more algebraic problem. And the way that we, in our work on air traffic control problems, what we typically, how we approach them at like a level of say a sector of airspace that has 15 aircraft, is we've got a hierarchical approach where there's a pairwise or small number of vehicle, you're sort of organizing them so each aircraft has, just one or two neighbors around it because you're routing along these routes. So you can do these lower dimensional reachability problems just to make sure that the collision is satisfied at the individual vehicle level. But then at the higher level, there's an algorithm which is scheduling the aircraft. Maybe it's around airports, or maybe it's just in a sector, and that's more of an algebraic problem. So as long as you've satisfied the density specification for links and regions, then you can just let the lower level collision avoidance system maintain the separation between aircraft. And that's actually how air traffic controllers, it's done manually, but that's how air traffic controllers do it manually. When they look at, how you should hold aircraft on the ground across the country because there's, weather event that's shutting down a region. So that affects capacity. And so you're satisfying capacity or density requirements, but then once you're within that, then you can use the more dynamic collision avoidance schemes.
Thank you. Janos Stepanovic, who needs no introduction to you, Claire, asked the question, are the computationally derived safety guaranteed accepted by certification authorities? In other words, can the method be used as evidence in assurance arguments, in argumentation? And he's got in parentheses, see the assured autonomy challenge.
Yeah, so this, hi Janos, good to hear from you also. I hope you're having a good time in your spring break. Janos is asking the question that pertains to using these kinds of certifications that we talked about of safety to like, can they be used as automated ways to certify safety of a problem or a problem and the assured autonomy. So there's a DARPA program that Janos and I and Xenophone are all on called Assured Autonomy, where the idea is to develop techniques that allow you specify the model and the specification, and even if there are machine learning components in the loop, how does one use these kinds of tools and techniques as a way to certify the behavior of a control system, for example, under a set of assumptions. So, I mean, we would like to, but I think that given what we said before about the behavior of machine learning components, we still have some ways to go when we think about the kind of large convolutional neural nets that are used in computer vision integrated into such a control loop. Janos and Xenophone's group have been doing really great work on, and also on integrating machine learning components into control loops like this.
Thank you. Thank you. Mark D'Angelo, who asked the earlier question, has a follow-up question here. Yes, he says, yes, thanks for your answer. So the smaller ones obtain shared position data from the ground control station. I think that was your answer to his question. Was the motion capture set up outside? Later, and then a comment, later the larger UAVs do the computation and collision avoidance on board in real time. And he comments, nice job.
Oh, thank you. Well, yeah, we didn't set the motion capture up outside. Outside, we're using GPS. So when we do our flights, we haven't done flights outside in a while, actually. We've been doing a lot of indoor flights. Even before the pandemic, the few years before the pandemic, we've been focusing on those sort of indoor lab experiments. But as I said, now, and actually now, of course, it's a lot easier to get approval to do flights outside. So we're setting up a station, a Richmond Field Station, which is a field station located near the Berkeley campus. It's kind of got a lot of World War II era buildings that provide great spaces for flying around, outside. We're setting up an outdoor network with the sensing and computation on board.
And Kim Wasson asked the question, what metrics with respect to reachability do you foresee being usable in developing criteria and means of compliance for aircraft system certification and approval?
Yeah, I think that's also, these are just great questions. I think that if we were to move with a, so I think it's more initially at the level of, well, there's two levels. So if it's aircraft certification, I think that being able to use tools like reachability to assess and to not only assess, but test aircraft. So things like that Boeing 737 MAX, the kind of behavior that was exhibited there because of the MCAS, it's an autopilot system that just, if they had studied, which is really hard, right? Enumerating the kind of conditions that could happen that could lead you to a failure like that. But reachability is just really a way of with the models that you have, getting a preview of the behavior of the system and asking, do these behaviors, could they result in an unsafe condition? So I think that there's a role for reachability both in autopilot certification as well as in the more air traffic control-like scenarios that we talked about. If we are to automate some functionality of collision avoidance between aircraft, right now it's done with air traffic controllers. It's called TCAS, for Traffic Alert and Collision Avoidance System. It's a system on board all passenger jets with more than 30 seats, which is kind of a last resort collision avoidance system that gives advice based on the call number of the aircraft to either go up or go down. But if we were to think more holistically about what is required in a system to implement a full collision avoidance system, then I would want a tool or a methodology that does this kind of preview to kind of ask, if we're automating this, are we taking into account all the scenarios that we need to take into account? And of course, even reachability, we have to enumerate what unsafe is ahead of time. But I think tools like this allow us, where we couple specification with dynamic behavior, are useful in doing this kind of preview in systems design.
And then Rakesh Khan asks, does this system have fault tolerance built into the system?
So does the tool have fault tolerance built in? I think that, well, the answer could be yes or no, depending on how, if we think about fault tolerance in the traditional way of, which is really enumerating the possible faults and then asking, do we have a way of avoiding the faults if we were to get into a situation where, or do we have a way of gracefully responding to faults if they happen? Then yes, I think that rather than built into the system, I think that reachability and that kind of dynamic preview is a way to address fault-tolerant problems, fault-tolerant control problems. Gautam Biswas is a old friend at Vanderbilt who works a lot on fault-tolerant systems, and I've learned a lot from actually, these early hybrid systems meetings that we went to together, where he really brought the point of view of what's been done in fault-tolerant control systems. But is fault tolerant built in a sense of, is there an automatic way now to enumerate all the faults? No, that's still an open problem, right? And that I think is a very good question, because that's an engineering challenge, is to try to, in any system, is to try to enumerate or ask ahead of time, what are the things that could go wrong? What reachability does do, though, is it moves that problem of, enumerating, possible, like asking, okay, are you going to be safe if that vehicle does this, or if it does this, or if it does this? By asking, are you safe for the worst possible action, then you're getting kind of a whole slew of possible behaviors in that one computation. And I realize that's not all possible faults. I don't think it ever will be, but to me, it's a better engineering way of approaching the problem than, say, simulation, for which you can only prove the property for the condition, like the initial condition and the parameters that you simulated for. Reachability allows you to do it for a set of conditions.
Okay, so another question. We're nearing the end of our time, so we'll just have one or two more questions. One from an anonymous attendee: are these techniques resilient to non-natural disturbances such as the one seen in adversarial machine learning? I think what they're asking about, you probably know
so
this.
If you try to do things like, okay, so the mathematical model asks you, what is safe and what is unsafe and what's your model, and then it will compute like the worst case action for that. But, however, what we've seen in adversarial machine learning are things like, well, for example, in pixels, are like really small disturbances in images that are hidden to the naked eye, but actually cause a big difference in the behavior of the learning algorithm. And that's not something yet that we've been able to characterize via reachability because of the dimensionality of the problem. An image, we'd have to be able to represent as our state space then each of the pixels as a state, and be able to propagate through the neural net behavior, what's happening with regions of the state space or regions of the images. And so I do, and several people working in reachability are working on these problems, but there's still a gap between the dimension of the problem that people have been able to solve and where typical image-based learning problems are. And that's a gap that I feel like over time we're gonna keep plugging away to be able to prove safe properties about neural nets, so that these kinds of adversarial disturbances can be characterized in a reachability problem. But because of dimensionality, we're not there yet.
Okay, we still have questions coming in, unfortunately, but I think we're going to run out of time. I'll ask one more question. Can you please compare the reachability analysis versus control barrier function on safe control?
Interestingly, we're just working on that. So I mentioned my colleague Kaushal Srinath, who works on legged robots. He works a lot on control barrier functions, and the two of us have been collaborating with we co-supervise a wonderful student who's in bold here, Jason Choi, who's working on a method to show that you can compute a particular finite time control barrier function using a Hamilton-Jacobi formulation. And I like that. I mean, I like it because control barrier functions and control Lyapunov functions are actually a very nice way to tackle dimensionality of a problem. They're a similar idea in terms of reachable. They lead to reachable or controlled invariant sets. They can. However, finding them is a challenge. And so showing that you can actually compute them via a Hamilton-Jacobi formulation is a nice start, I think. So I don't know a full answer to the question yet. It's a very interesting question, and I think us and there's others around that are and perhaps the author of the question is working on that too.
And then Philippe Fauché had one more question. And he said, what will it take to make humans trust truly autonomous systems? I think that's more of a philosophical.
Wonderful question to end on and have some champagne, because I think that's a question that it's going to take time and experience, not just like mathematical tools, right? But a whole bunch of confidence and experience in using these systems and having them fail and having them recover from failure and understanding those. Yeah, wonderful question.
Okay, well, let's wrap it up. And we want to thank you again, Claire, for a wonderful, wonderful talk and for responding to all of the questions. I am going to now close. It may have been closed for me, but thank everybody for their attendance.